Welcome to This Explainer. Today, we're undertaking a really fascinating shift in perspective. Before we even think about writing a single line of code and way before we try to train some complex neural network, we've got to learn how to think like an energy engineer. Because the truth is, you just can't build effective AI for the physical world until you deeply understand the physical reality that generates your data. We're talking about the massive, breathing entities we interact with every single day, buildings.
So, what energy data exists around you right now? Seriously, I want you to look away from the screen for just a second. Look around the room you're sitting in. What's quietly humming in the background? What's silently measuring the world around you?
That space you just looked at, it is absolutely saturated with invisible data streams. You've got electricity running through smart meters, maybe a solar inverter up on the roof, HVAC sensors tracking the air, lifts pulling massive amounts of power, and maybe even EV charging stations out in the parking lot. Most buildings today are already smart enough to continuously collect all of this data. The problem? They simply aren't smart enough to actually use it. And that is exactly where we come in.
Which brings us to our first core concept, the context imperative. Basically, data equals measurement plus context.
Take a look at this. 120. Just a giant, naked number. Let that sink in for a second. If a database feeds this raw number to your machine learning model, what on earth is it supposed to do with it?
Because what context is missing here? Is this an instantaneous reading, an hourly average? Are we talking about daily consumption for one single floor or the whole shebang? Is it just the HVAC or lighting only? Without answering these questions, that 120 has absolutely no value to an AI model. If you feed uncontextualized data into an algorithm, you're just going to get perfectly calculated, mathematically sound garbage. You have to know the physical reality behind the digits.
Moving on to our next section, quality and modality, the shapes of data.
Okay, this right here is a massive trap that data scientists fall into. On the left side, we've got 10 years of historical data. Sounds incredible, right? Well, actually scratch that. It's in 15-minute intervals with zero occupancy records, no weather data, and no equipment labels. It's basically a decade of blind spots. Now compare that to the right side. Just one single month of data, but it is incredibly rich. 1-minute intervals, perfectly mapped with occupancy, local weather, and exact equipment states. You might instinctively think more is better, but trust me, 1 month of deeply contextualized data is a total game changer compared to a decade of bad, isolated data.
And you know, data isn't just neat rows and columns. Just look at the modalities here. Sure, you've got tabular data like utility bills and time series data like minute-by-minute temperature. But look deeper. We're talking images from thermal cameras showing heat leaks, graph data mapping out microgrid topologies, and even text from maintenance logs and BMS alarms. A truly robust AI model often needs to weave these wildly different shapes of data together.
But here's the catch. Even with perfect data, the context completely shifts depending on the domain. Look at commercial spaces like hotels or schools. Their AI assumption drivers are fundamentally based on occupancy and timetables. Switch to an industrial dairy plant, suddenly it's entirely production-driven. Or a digital data center, human occupancy barely matters there because it's almost entirely IT load-driven. You could use the exact same AI architecture, but it requires completely different assumptions.
All right, let's get into the next piece of the puzzle, the audit, trusting your repositories.
So where do we actually get all this? These are the primary repositories for open energy datasets. You've got the heavy hitters like OpenEI, the Building Data Genome Project, ASHRAE, and UCI Energy Datasets. You'll also see Zenodo and Figshare. Now, a quick heads up on Kaggle. It's fantastic for exploring and practicing, but you've got to be super careful. It is generally for exploration only, not as a primary scientific source, since the provenance isn't always rigorously verified.
And listen, once you download a dataset, you can't just blindly trust it. You have to relentlessly audit it using these criteria. How's the documentation? Do you actually know the building area or the HVAC type? What about provenance? Is it from a highly accurate utility meter or a glitchy local smart meter? Check for completeness. Are entire weekends mysteriously missing? And crucially, format. Are we talking kilowatt hours, kilowatts, tons of refrigeration, or Celsius? You need to know exactly what every single metric represents.
Which naturally leads us to our next section, the pitfalls of trust, or when sensors lie.
Honestly, it's almost comical when you first see it, but you will routinely find absurd metrics in the wild. On the left here, negative 500 kilowatts of power consumption. Unless that building magically turned into a massive power plant, no way. Or a room temperature of 145 degrees Celsius. Then, on the right, you get logical impossibilities. The building is fully occupied, but the HVAC is totally off in midsummer, or zero energy consumption for 6 straight months. These aren't just quirks. They are sensor drifts, manual resets, or technicians literally swapping labels by accident.
And what about missing data? This is absolutely crucial. A missing energy value is almost never just a zero. If you fill blanks with zeros, you're wrecking your model. A missing value is an event. It means a sensor went offline, or you had communication packet loss. Maybe it was scheduled maintenance, a physical power outage, or a total sensor failure. You've got to model the absence of data just as carefully as the data itself.
Even basic statistics can lie to you if you aren't careful. Look at this breakdown between weekday and weekend energy use. If you just grab the mean across the whole 7-day week, it's going to suggest a constantly high consumption around 2,000. But the median? That reflects a true, typical weekday. Meanwhile, your maximum value highlights your peak demand. The stat you choose to feed your AI completely depends on the specific engineering question you're asking.
Let's bring it all together in our final section. Real-world impact, AI applications in action.
When you finally have that pristine, audited data, AI stops being just a buzzword. It becomes a powerhouse tool. We're talking real capabilities like advanced energy forecasting, precise load prediction, and predictive fault detection. Imagine catching a failing chiller plant weeks before it actually breaks. We can optimize maintenance, dynamically predict occupancy, and run smart demand response to save an absolute fortune on utility bills. And it's amazing to see how AI pivots for hyper-specific, real-world queries. In a hotel, it might ask, can we invisibly reduce HVAC without affecting guest comfort? Over in a mall, can we safely slow down the escalators during low foot traffic hours? Or in a hospital where the stakes are literally life and death, can operating theaters be conditioned completely differently than the waiting areas?
The applications just keep going once you respect the domain context. For schools, should the HVAC run during an unexpected vacation day? In data centers, can we actually shift the server workload itself to physical racks that need less cooling right now? Or out on a dairy farm, can we intelligently schedule milk chilling to align perfectly with renewable energy from solar panels? The physical context always dictates the AI strategy.
So what energy dataset around you could become a publishable research dataset? Look at your campus HVAC, the occupancy patterns in your local library, or the solar panels on a nearby roof. That invisible hum of data is literally everywhere. The question is how you're going to take that raw, chaotic info, apply an energy engineer's mindset, and turn it into a breakthrough. Thanks for joining me on this explainer, and I challenge you to go find out.